All right, good morning, everybody. So I want to quickly review what we were talking about in the previous class before we move on, because it's been some time since we talked about these things. So we were talking about the relationship between classes in the previous lecture. So when you make a class and it has fields that are references to other objects, you now have to consider what relationship do your classes have with one another. So the simplest kind of relationship between two classes is called dependency. Right, so remember, dependency models the uses relationship. Right. The class X depends on the class Y if Y appears anywhere. Right. And so dependency is it's an obvious kind of relationship, right? Its name even suggests exactly what the relationship is, right? So if you are writing a class, X in this case, right, and somewhere in the class you mention another class Y, then X depends on Y, right? In the implementation of X, you are relying on this class Y to help you implement X. X has a dependency on Y. Right. So there's a stronger relationship called association. Right. So association models the has-a relationship. By has-a, I mean has a reference to relationship. Right. And so again, if you look at the name and and the relationship that it represents, it should be obvious what is the implication of this relationship. Right. And so if you have a class X, right, has an association with, if X has a field of type Y. So when you go to implement your class X, you decide one piece of information that every X object needs is a reference to a Y object, right? In other words, X has a field of type Y, then you have an association relationship. Right. It can also be the case I guess I should indent this. That Y has a field of type X. Right? And so in association, it might be the case that this class Y also has a field of type X. Right? So X has a Y, Y has an X. Right? And so in other words, association is allowed to be a two-way, can be a two-way relationship. All right, so that's what association means. Now, dependency may also, it's also true with dependency. Right? So if class X uses class Y, it may also be the case that class Y uses class X. Right? That's an example. So an example of that from the standard library would be object and string. Right? So if you look in the object class, you'll see there's a toString method. So it needs the string class to work. If you look in the string class, you'll see there's many methods that rely on the class big O object. So string needs the class object to work. It is the case in Java that every class requires big O object. Right? So in Java, every class has a dependency. Right? And actually, in Java, the relationship is actually stronger than that. Right? So it turns out there's a much stronger relationship than dependency with object in Java. Right? But for the time being, this is true. Well, this is always true. For the time being, this is sufficient. Okay, so what other types of relationships can you have? So there's three other relationships that we're interested in this course. I'll get to two of them today, I think. The third one won't show up for a couple of lectures yet. So the two relationships that I want to talk about today are called aggregation and composition. And I guess I should point out now that many people consider that aggregation to be not significantly different than association. All right, so I'm going to use a particular definition of aggregation that turns out is a stronger form of association. Right? Again, many people will disagree with this, but that's okay. Right? So aggregation and composition, again, they are relationships between objects. Right? So both terms describe a has-a relationship. Right? So far that sounds exactly like association. Right? But there's an extra piece of information here that you have to, there's additional features of these relationships that association does not have. So if you imagine the university, you might think that the university is a collection of faculties, right, or a collection of departments or something like that. Right? If you consider a department, I think it's the case that every department has a collection of more than one professor at Queen's. I don't know if there's a department or well, there's certainly no faculty, but I don't know if there's a department made up of only one professor. Anyway, a department you can think of as having a collection of professors, right? And so these are both has-a relationships, right? Okay, so composition and aggregation, composition implies what's called sole ownership. Right? So for example, if the university were to go away, right? So if Queen's was to magically disappear tomorrow, all of its departments also go away, right? The Department of Computing Science does not exist without the university. So university would be a composition of departments, right? The university owns its departments. Aggregation does not imply sole ownership. So if a department at Queen's goes away, then it is not the case that the professors also go away, right? And so for example, if say the School of Computing were to disappear tomorrow for whatever reason, it's almost certainly the case that the professors in the department get dispersed to other departments. Right? And so the departments don't own the professors, right? So we might say that a department is an aggregation of professors. Right? Now here, both aggregation and composition are one-way relationships. So that's the difference between aggregation, composition, and association. Right? Association is allowed to be two-way, right? Aggregation and composition are not allowed to be two-way. Right? This might be a bad example here, the professor and department one. You could probably argue quite successfully that this is really an association. Oops, sorry. All right, so let's look at aggregation first because it's the simplest of the two relationships. And the nice thing about aggregation and association is that you could all implement the class using aggregation or association today because it looks no different than any class that you've implemented so far. Right? So I'm just going to make up a class called person just for the purposes of this lecture. We're never going to see it again. Many introductory courses use a similar kind of class, right? Employee or something like that. Right? So every person has a name, every person has a birth date. Right? Now notice their fields, right? They're both of reference type. Right? So the name is an object of type string. Right? The birth date is an object of this class called big D date. So the class date is found in the package java.util, and it represents a point in time. Right? If you were to draw the UML class diagram showing the name of the class in the fields, it would look something like the thing on the right. Right? Box, person, right? Minus name, minus birth date, colon string, colon date. Right? So every person has a name, that is a string. Every person has a birth date, that is a date object. Minus sign indicates the fields are private. Okay, so if I was to ask you to implement this class, I think everybody here should be able to implement this class very easily. Right? It looks no different than any class you've implemented so far. You throw in a constructor, right? You can make a person having a specified name and specified birth date. Right? You would probably write something like this name equals name, this birth date equals birth date. Right? If I ask you to add a method that returns the name, you would probably add a method called getName or name, right? And it simply returns this.name. Right? And the exact same thing is true of the birth date. Right? You would just return a reference to the internal birth date object. Right? And so I think everybody here could do this. Right? It's just a class with some fields and some accessor methods. Right? So that example right there is an example of aggregation. Right? So I guess the first question is why is it not association? Right? So remember, association is allowed to be a two-way relationship. Right? Does the string class have a reference to the person? Absolutely not, right? Whoever implemented, right? So we're implementing person, right? Somebody else implemented string and date, right? So whoever implemented string has no idea that this person class exists, right? Therefore, the class string, there's no way that string could have a reference to a person, right? Does date have a reference to a person? Again, no, right? And so this relationship really is one way, right? Person has a string, person has a date. So this is aggregation. So notice that the constructor doesn't actually make a new string or a new date object. Right? So you go back to the constructor, right? We're writing this name equals name, this birth date equals birth date. Right? So remember in Java, all reference variables are storing references to objects. They don't store the objects themselves. Right? So when you write this name equals name, right? This name is a reference to the exact same string object as the parameter name, right? And this birth date is a reference to the exact same date object as birth date, right? The person object has not created a new string and has not created a new date to store its own name and birth date. Right? And so the name and the birth date objects are both shared with the caller. So whenever you see client on these slides, I just mean the caller, right? So whoever made the person object, right? So whoever made the person object, they have a string and a birth and a date object, right? Because they need them to call the constructor, right? The person object that gets created has the exact same name and birth date object, right? It has a reference to the exact same name and birth date object. Right? So both the caller and the person are holding references to the exact same name and birth date. So if the caller somewhere makes a string S and a date D, and then a person using S and D, right, what ends up happening is the following. Right? Okay, so here's the caller. They have a variable S. This is the name. Right? So the name is a string, so it's sitting here somewhere. Right? So somewhere in memory there's a string object. Right? They have a date object. So apparently that's sitting at address 350. So in memory somewhere there's a date object. Right? They make a person object. Right? So they call the person constructor. The constructor runs. Right? It copies the person. It copies the person class, plunks it somewhere down in memory. So there's your copy. Right? And then it fills in the name and the birth date. Right? And so the code is this name equals name. Right? So there's this name. Right? When you say this name equals name, you just copy whatever, sorry, this name, yes, equal, you just copy that value there. Right? And so the name becomes a reference to that string object there. Right? And this birth date equals birth date, so in this case it's D. Right? So whatever value is here, you just copy into here. Right? And this says that the this dot birth date refers to that date object. Right? And the caller, they have a date reference that also refers to the same date object. Right? And so both the caller and the person object, right, are sharing references to the same objects. Right? There was no second date object created. There's no second string object created. So what happens if the caller decides to change their date instance? So date is a bit of a funny class. But I'm going to use it a lot because it's useful to illustrate the composition and aggregation. So date is a mutable type. So it represents a point in time, and if you have a date object, you can change what point in time it refers to. So you can change its month, its year, its date, its hour, minute, second, and so on and so on and so forth. Right. So there's the code from before. Right. Now remember, the caller has this reference D to a date object. So for example, they can change the year to 1995, they can change the month to November, yes, and they can change the date to 3, so November 3rd, 1995. Right? So they're changing their date object D, right? Now if you ask the person, right, hey, what is your birth date? That now prints out November 3rd, right? And so the caller has changed their date object. Right? And a consequence of that is that the person now has a modified birth date, which you might find is weird, right? You might think that, hey, the person object probably should be taking care of its own birth date object, right? Someone shouldn't be able to just change their reference, right, D, right? And suddenly the person's birth date changes, right? That may not be what you want to happen. Right? But because of the way we've implemented the person class, right, that date object that the person has, right, or the reference to the date object that the person has is exactly the same as the reference that the caller has. Right? They both have a reference to the exact same date object. So the caller can change the date using D, right? And the person object, P, now gets this modified birth date. Similarly, right, in the person class, maybe there's a method that changes the birth date of the person. Right? And so if the person class changes its reference, right, so if it uses its reference to change the date, then the caller, when they use their reference D, they also see the changed date. Right? So the caller can change the state of the date, and the person object can change the state of the date. Neither the caller nor the person object owns the date object. Oops, sorry. Right. Now, you might look at the name and you say, hey, the exact same thing is true of the name. Right? Both the caller and the person object, they have a reference to the same string object. But the thing you have to remember about string, right, is that it's immutable. Right? Once a string object is created, the characters in the string can never change. Right? You can't change its length, right? You can't change the characters, right? So strings are immutable in Java and in Python. Right? So there's no way for the caller to change the string that represents the name. And similarly, there's no way for the person object to change the string that represents the name. Right? And so if you can, it's often a good idea to use immutable objects to create your classes. Right? So they make good building blocks for other objects. Right? You never have to worry that so if you use a string, for example, as part of your state, you never have to worry that that string is going to change on you from outside the class. Right? So you can freely share references to immutable objects, and you never worry about their state changing. Right? So once someone makes a string, that string always represents the same sequence of characters. It doesn't matter if there are 50 references to the same string object, right? That string object never changes. That's not the case with the date object, right? As soon as someone else gets a reference to your date object, that other person or object can change the state of that date. Okay, so if you want to draw the UML class diagram for aggregation, you would draw it like the following. So here's our person class, right? We know person has a string, right? Person has a date. So in association, you would just draw a solid line between person and date, and you would just draw a solid line between person and string. Right? Here we have aggregation. So aggregation is indicated by an open diamond on the person object in this case. Right? So often you'll see this called the whole object, and the date and the string would be called the part objects. Right? So a person is made up of a date and a string. So the person is the whole, and the date and string are the parts. Right? So the diamonds go on the whole object. They are open diamonds. A closed diamond means something else in UML. Right? And so this diagram simply says person is an aggregation of one date, and person is an aggregation of one string. All right, here's another little aggregation example. So first, I'm going to run the code first and show you what's going on. Oops, wrong. Here we go. Okay, so this is a bouncing ball. Where'd it go? There we go. Hey, what happened? Oh, sorry, wrong class. Here it is, man. There we go. Okay, so this is a bouncing ball example. So that ball is an object called a projectile. So it represents, if you've taken first year physics, this is just a projectile falling under the influence of only gravity. And so that's a projectile. A projectile is made up of a position, right? So at any one point in time, the position represents the location of the ball, right? And it's also made up of a velocity, right? So the velocity is a vector that indicates what direction the ball is moving in and at what speed it's moving in. Right? As it falls under the influence of gravity, the velocity vector grows in magnitude. Right? If you haven't taken physics yet, don't worry about it. It's not a big deal. Right? All that matters is that a projectile is an aggregation. In this case, it's an aggregation of a point object and a velocity object. right? If you have taken physics, those are just the equations of motion that this thing is using, right? If you haven't taken physics, again, don't worry about it. It's not a big deal. And so it's the exact same picture as I just showed you before, right? That picture is exactly the same as that picture there, right? It's just that the names of the classes have changed, right? So projection is an aggregation of one point, and it's an aggregation of one vector, right? So the point represents the position, the vector represents the velocity. How do you implement this thing? Well, guess what? It looks exactly the same as the person class, except the classes have changed, right? So instead of person, it's now projectile. Instead of string, it's now point 2, right? So that's the position of the projectile. And instead of date, it's now vector 2, which is the velocity of the projectile. There's the no argument constructor. So your no argument constructor has to set the position and velocity, right? So it has to set these fields here, right? Whoops, sorry. For the no argument constructor, you have to make a new object. There's no other way to do this, right? You have to set the position and velocity to something, right? So here we're going to make a new point. So it's going to be 0, 0. We're going to make a new vector, which will also be 0, 0 in this case. So it's just so the position of the projectile is the origin, and it's not moving. So its velocity is 0. Its get position method looks exactly the same as get name, right? As get name would look like in the person class, right? You just return this dot position. Right? And guess velocity just returns this dot velocity. Right? Set position here, you could, this one returns the current position, right? And then changes the, and then changes the current position to P. Right? So remember the old position, set the current position to P, and then return the old position. Get velocity does the exact same thing, right? Remember the old velocity or the current velocity. Set the velocity to v, and then return the old velocity. Right? And finally, there's move. So move implements that equation, these two equations here. Right? And so if you work your way through this code here, you can convince yourself that that, in fact, is what move is doing. Right? But notice that all it's doing is it's changing the position and velocity of the projectile. Right? So implementing that thing is pretty easy. The only quote-unquote hard thing is the move. Right? Otherwise, the class looks exactly the same as any class you would implement in this course so far. Right? There's nothing different here. Right? So what are our fields? So the fields are, well, there's a vector and there's a point. Right? But these are simply references to objects provided by the caller. I guess I should clarify that point. It's not exactly clear. I guess I'm not showing you where to go. Oh, it's not here. Okay, so if you were to implement a constructor where the caller can specify the position and the velocity of the ball, of the projectile, right? You would write a constructor that looks like that, right? So the caller specifies the position, they specify the velocity. How would you implement it? Well, it's pretty easy, right? This dot position equals POS. Right, and this dot velocity equals VEL. Right, so if you have that constructor there, right, what are our fields, position and velocity? Well, they're just references to somebody else's position and velocity. Right. The accessor methods, they simply hand out references to the internal point and vector objects. Right? So to get the position of the ball, you just simply return this dot POS, and to get the velocity of the ball, you simply return this dot VEL. Right? The mutator methods, they simply set our fields to references that were provided by the caller. Right? So set position, so there's, we're set. So set position simply does that. Right? Sets our field POS, to refer to the exact same point as P. So whatever P refers to, POS now refers to, right? And whatever V refers to, VEL now refers to, right? So in other words, the projectile, in most cases, never has its own point object, and it never has its own velocity object. that the projectile has, so the projectile never has exclusive access to its own point and velocity. Right? Its point and velocity fields are simply references to objects that anybody else can get a reference to. Right? So we say that the projectile fields are simply aliases. Right? So what's an alias? An alias is just a different name for something. Right? So in our class projectile, right, POS is just the name of some object somewhere in the world, right? And VEL is just a name for some object somewhere else in the world, right? Somebody else probably has a different name for that object, for the position and velocity objects. Right? Here. Oh, sorry, here. Okay. So if you were to write a main method somewhere and make a projectile, right? In the main method, we have a point and a vector representing the position and velocity. Right? To make the projectile, I'm going to make an object called ball, right? Call the constructor and then call set position and set velocity. Oops, sorry, that's wrong. Typo there. Right? And set the position and set the velocity to that object and that object there. Right? And so if you were to draw the memory diagram of this thing, right, it's the exact same memory diagram that you would have drawn for the person class. Right? It's the exact same thing. Right? There's your point, right? There's your vector, right? So that's the point that the client has a reference to, right? They have a reference to that point there, right? The caller has a reference to that vector object here. Right? The caller then makes a projectile object called ball. Right? So there's the projectile object. Right? Another typo, sorry. Because the typos are here because I changed the implementation of the class when I was after I made the slide. Okay, so the projectile object, it has a field called POS, right? And it's just a reference to that point object here, right? And VEL is just a reference to that vector object up here, right? So caller, right? Projectile object, right? But only one point object and only one vector object. So in other words, the caller and the projectile, they're sharing these two objects. Right. So if you ask the ball, right, what is the position of the ball? Right, that'll return a reference to, well, it'll return this .pos. Right. If you then ask, is the ball position the same object as POS? Right. So in other words, is this value here, right, or is this reference here the same as that reference there? Right? And the answer is yes. Right? Right? That value there is exactly the same as that value there. Right? And the same is true of the velocity. Right? That value there is exactly the same as that value there. So, oh, sorry. Yes. So ball position is equal to that, right? And that is equal to that. Right? Okay. So what happens if the caller uses their reference to change the position, to change their point, right? So using that reference there, right? If you change the position of that point to -99 and -22, right? So this is the funny part here, right? So what happens when you print out the value of ball POS, right? Notice back here we had to call a method to get the position of the ball, right? I'm not calling that method again, right? I'm simply printing out the state of ball POS, right? This will print out -99 and -22, right? And so, right, so it prints out the changed position, right? Why does it print out this changed position, right? So when you print out ball POS, right, you're printing out you're calling toString on the object at address 250. Right? That object has changed. Sorry, here, right? So the caller changes the state of that point object here, right? Ball POS is exactly the same object or refers to the exact same object that POS refers to, right? And so the value of this variable has changed even though you haven't done anything to do, even though you haven't apparently done anything to change that variable, right? We didn't call a method using ball POS, right? We didn't write ball POS equals something, right? But by changing POS, that causes ball POS to also change, right? They're simply references to the same object, right? So when you call set on POS, right, that object, the state changes, right? Ball POS refers to that object. So when you print out ball POS, you get the changed object, you get the changed point to state. Right. All right, so what does this mean? So if you implement an aggregation, you have to understand that you are implementing an aggregation. Right. So if a caller gets a reference to the position or velocity of the projectile, right? So if they somehow get a reference to, if they get a reference to the position or velocity of the projectile, right, then they can use that reference, right, and modify either the position or the velocity, right? They can change the point or the vector. When they do that, the projectile's position or velocity changes, right? And you never have to ask the projectile object itself to change its position or velocity, right? So in other words, you never have to write ball.setPosition or ball.setVelocity to change the position or velocity of the ball. And you might think that's weird, but it's not. Well, I mean, it kind of looks weird, but it's not. But there's no error here, right? There's no flaw in our implementation, right? It's simply a consequence of choosing to use aggregation, right? So you have to understand that when you're using aggregation, right, you are basically saying your object is willing to share its internal state with everybody else. Okay, so if that bothers you, right, so you might say, hey, look, it doesn't make sense that the position of the ball can change if you don't ask the ball to change its position, right? So if you want the ball to control its own state, right, you can't use aggregation, right? You have to use composition instead. Okay, so what does composition mean? So recall what it means. It means if x is a composition of a y, it means x has a y. So remember, association, aggregation, and composition all model has a. Right? Also remember, composition is the stronger form of all of these. Right? It also means x owns its y. Right? And so in other words, x is not willing to share its y with anybody else. Right? Which I'm going to phrase in the slides as the x object always has exclusive access to its y object. Right? It's never willing to share its internal y object with anybody else. Right? So what does this mean exactly? It means it's not willing to hand out a reference to its internal y object. Right? So your constructors for your class, right, they can't simply write this y equals y, where y is a reference provided by a caller. Right? They have to copy the object that the caller is passing to the constructor and make a new y object. Right? Your accessor methods can't simply return this dot y. Right? They have to make a copy of the y object and then hand back a reference to the copy. Right? And finally, if there's a method that lets you set the y object of an x object, right, you can't simply write this y equals y. Right? You have to make a copy of the incoming y object and then set your internal reference to equal the copy. Right? So create new objects here, you have to create new y objects here, you have to create new y objects here, right? And so these new y objects are called defensive copies. Right? They're copies because you have to make new objects, right? They're defensive because you want to make sure that the x object has exclusive access to its y object, right? You're not willing to share a reference to your internal y object with anyone else. Oops, sorry. Okay, so in your no argument constructors, they're not normally different between aggregation, composition, and association. Right? No argument constructor for x has to make a y object. Right? There's no choice. Right? So you're going to write this y equals new y, blah, 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 right? Depending on what the y constructor looks like. This isn't really a defensive copy. It's just how you implement a constructor. Okay, so this is where the defensive copy becomes important. Right. So remember, x is x has a y object. So if you let the caller pass in a reference to a y object, right, that you want the x object to use, right, you can't simply write this y equals y. Right? You have to copy the incoming y object first. Right? So here I'm assuming there's a copy constructor for y. That's not always the case. Right? If there's not a copy constructor, you have to copy the incoming y some other way. Right? If there's no way to copy y, or if there's no easy way to copy y, then you probably can't use y in a composition. Right? You have to make the defensive copy here. Right? If there are any preconditions on the state of y, right, you're now going to check the copy, right, to make sure that the copy satisfies any preconditions. Right, so check y is just some method that is just some made-up method that checks whether or not the incoming y object is suitable. Right? If it passes the check, right, or if it passes validation, then you can write this y equals copy y. Right? So you've made your own y object, right, and you're going to set this y to refer to your brand new copy of the incoming y object. Okay, so why do you have to do that? I should scratch that. So why is the copy required of the incoming y object? Right? So remember what composition means. Composition means every x object always has exclusive access to its own y object. Right? If you write this y equals y, what are you saying? Right? You're saying the internal y object is the exact same object as the object that was passed into the method. Right? So the x object no longer has exclusive access to its own y object, right? It's sharing it with whoever called the constructor. Right? So both the caller and the x object share a reference to the exact same y object, right? And now you have a problem, or now you potentially have a problem, right? It's no longer a composition. So whenever you end up sharing the internal y object, right, that's called a privacy leak when you're talking about composition. Right? So one way to think about a composition is that the internal y object is private. Right? Only the x object itself should have access to that y object. Right? If somebody else gets access to that y object, right, that becomes a privacy leak. Okay, if you have a copy constructor in your class, right, so in other words, if you can make a copy of another x object, right, guess what you have to do in the copy constructor? You have to copy the other x object's y object. Right? So remember, in composition, every x object has exclusive access to its own y object. Right? So if you were to write this y equals other y, right, this is no longer true. This y equals other y means two y objects are willing to share the same x object, right? And that's not a composition. Right? So again, you have to copy the y object belonging to the other x object. Right? So there's your defensive copy yet again. Notice there's no validation here. Right? So why don't you have to validate the other object's y object? Right? Well, if you have another x object, right, that other object has already validated its y object. Right? So there's no point in revalidating yet again. Right? So what happens if you write that? Right? So when you write this y equals other y, right, notice there's no new here. Right? That's the easy way to determine what's going on here. Right? You're not making a new y object for the newly created x object. Right? This y equals other y simply means that the y object belonging to this object is the exact same y object belonging to the other x object. Right? You now have two x objects that are sharing their internal y objects. Right? So every x object created with the copy constructor ends up sharing its y object, right? And that's a privacy leak. Right? If one x modifies its y, right? Every X object ends up seeing the modified Y object, right? Every X object that was created using the copy constructor ends up seeing the modified Y object, right? So again, privacy leak. Okay, so if you decide that in your projectile class you want it to have you want the ball to control its own position and velocity, right? You now have to go in and start to do surgery on the class, right? So for example, where's projectile? Okay, so here's projectile. There's our no argument constructor. You don't have to change anything in the no argument constructor. We're making a new point and new vector every time, right? This is our, here's our constructor that takes in a position and velocity, right? This is incorrect, right? You can't write this position equals position and this velocity equals velocity, right? You have to make a copy of that, right? And assign the copy to this dot position, right? There's no validation here, so we don't have to worry about that. So fixing this is relatively straightforward. We can simply do that. Right, point 2 has a copy constructor that will copy another point, so we can just use the copy constructor for point 2. The same is true for vector 2. Right, so make sure to copy the incoming objects, right, and then assign your fields to refer to the new copies. Right, there's our copy constructor, right, that says this projectile is willing to share its position with the other projectile, right? And this projectile is willing to share its velocity with the other projectile, right? If you want them to be independent, right, make the copy. Like that. Right? And so that updates the copy constructor to now use composition. What about the accessors and the mutator methods? Well, guess what? It's the same story all over again, right? So if your X object has a method that returns some information about the Y object or returns a reference to the Y object, this is a problem, right? So in other words, if you wanted to return the internal Y object, you can't return a reference to your Y object, right? You have to return a reference to a copy of your Y object, right? If you don't, right? So if you just return this dot Y, right? What have you done? You've just handed out a reference to your Y object, right? So the X object no longer has exclusive access to its Y object, right? Again, it's a privacy leak, right? How do you fix it? Is that on that slide? Yes. So how do you fix it? Well, pretty straightforward for projectile, right? Instead of returning this dot position, right? You return a copy of the position. So return new point 2. And the same is true of the velocity, right? New vector 2. So there's your accessor methods updated. And of course, the same thing is going to be true for the mutator methods, right? So a mutator method changes the state of the Y object, right? So here we've got a method set Y. That sets our Y object to a caller specified Y object, right? The correct way to implement this in a composition, copy the incoming Y object, right? It's the exact same as the constructor, right? If there are any preconditions on that, validate the copy, right? Then assign your internal field to refer to the copy, right? If you write that, right, you're saying that your Y object is the exact same Y object as what was ever passed into the method, right? So you're sharing your internal Y object with somebody else, right, with the caller. So again, you have a privacy leak here. How do you fix it? Right, again, it's the same old story all over again. So here's set position, right? I can't write this POS equals P, right? I have to make a copy of P. I have to make a copy of P, right? And set this POS to the copy, right? Similarly here, I can't write this VEL equals V. I have to write this VEL equals new vector 2, right? Copy the incoming object, right? Assign your internal reference to the copied object, right? And I think that updates the projectile class. Okay, so notice down here in the console, there's this 3 being printed out. And there's lots of them. And so what that was printing out was the number of point objects that were created by our program, the bouncing ball program from before. Right, so it looks like there were 3 point objects created in total when I ran that program before. You might think there'd only be 1, but because of the no argument constructor makes a point, and then the bouncing ball class itself makes a point, so there's 2. Right? And then when you set, it has to make a 3rd point to actually set the position of the ball. So in total there are 3. I've now changed the projectile class, right, to use composition. So if you were to run the bouncing ball program again, right, this time it's using the updated projectile class. Right, so we'll run that. It looks like it's the same, but you might notice it's running an awful lot slower. Right? It should be. Right? I think it's pretty obvious that that ball is moving around at a slower rate. Right? I haven't touched the bouncing ball program at all. Right? And remember, there's only 1 bouncing ball here. Right? You can imagine in a video game, in a modern video game, there might be thousands or millions of points flying around on the screen. Right? Let's see what happens over here. Oh, look. So that program's only been running a few seconds. Right? And what has that program done? It's created over 7,000 point objects in the time that I was running that program. Right? That's a lot of point objects, given that there's only 1 thing moving around on the screen. Right? In an ideal world, you would only need 1 point object, right? That represents the position of the ball. But here, we've got 7,000 something. Right? Why do you have 7,000 something? Right? It's because every time the bouncing ball program needs to get the position of the ball. It needs to get the velocity. It needs to get the position of the ball. It also needs to get the velocity of the ball to update the position. But anyway, it needs to get the position of the ball. Every time you return the position of the ball, you have to make a new copy of the internal point, right? And so you end up, right, constantly making new points simply to get the updated position of the ball, right? And so you end up making lots and lots and lots and lots of lots of point objects. All right, so this is the price of using composition, right? Composition requires that you make defensive copies of stuff, right? Well, what is the price of making these copies, right? Point 2 only has 2 double fields, right? It's not a lot of memory to represent a point object, right? But every time you make a new point object, right, the virtual machine has to allocate memory for that point object, right? When you're done with the point object, the virtual machine has to remove those point objects from memory. And all of this stuff takes time, right? So every time you make a defensive copy, that takes time and memory to make the copy, right? You then have to get rid of all the copies at some point. So that also takes time to garbage collect those defensive copies, right? So the bouncing ball program calls the move method, followed by get position every 25 milliseconds. Right? And so for every second that you run this thing, you're making 40 points, at least 40 points, right? Just to move the position of 1 ball. And you can see that even though there's only 1 ball moving around, it slows down the program. And so the price of composition, there is a price to be paid for composition, right? It's not free. And so for things like the bouncing ball program, you would probably decide to live with aggregation, right? So you'd probably prefer not to make these copies all the time, right? And live with the fact that somebody else might be able to change the state of your projectile. Right. All right, so I think we're out of time for today. So we're going to talk a little bit more about composition in the next lecture, and I'll explain when is it that you have to use composition